Hi, in this video we are going to see about the impulse and step response analysis of a second order system. The effect of location of poles and zeros on the transient response of first order system already discussed. Compared to the simplicity of a first order system, a second order system exhibits a wide range of responses that must be analyzed and described. Being a first order system parameter sim t, k simply changes the speed and offset of the response, whereas changes in the parameters of a second order system can change the form of the response. A second order system can display characteristics much like a first order system, or depending on component values display damped or pure oscillations for its transient response. Consider the following block diagram of closed loop control system. Here an open loop transfer function omega n square divided by s into s plus 2 tau omega n is connected with a unity negative feedback, where cs of s divided by r of s equal to omega square n divided by s square plus 2 del omega n s plus omega square n, where omega n is undamped natural frequency of the second order system, which is the frequency of oscillation of the system without damping. Tau is the damping ratio of the second order system, which is a measure of the degree of resistance to change in the system output. The undamped natural frequency and damping ratio of the following second order system is shown. For example, C of s divided by r of s equal to 4 divided by s square plus 2s plus 4. Compare the numerator and denominator of the given transfer function with the general second order transfer function. In this, omega square n equal to 4, where omega n equal to 2. S square plus 2 tau wn s plus omega square n equal to s square plus 2s plus 4. In this, 2 tau omega n s equal to 2s, tau omega n equal to 1, and tau equal to 0.5. C of s by r of s equal to omega square n divided by s square plus 2 tau omega n s plus omega n square. The two poles of the system are minus omega n tau plus omega n square root of tau square minus 1 and minus omega n tau minus omega n square root of tau square minus 1. According to the values of tau, a second order system can be set into one of the four categories. The first one is overdamped, when the system has two real distinct poles, where tau greater than 1. Second one is underdamped, when the system has two complex conjugate poles, tau lies between 0 and 1. Third one is undamped, when the system has two imaginary poles, in this tau equal to 0. And fourth one is critically damped, when the system has two real but equal poles, when tau equal to 1. Second order system. Transfer function of the closed loop control system having unity negative feedback as C of s by r of s equal to g of s divided by 1 plus g of s. Substitute g of s equal to omega square n divided by s into s plus 2 tau omega n in the above equation. We get C of s by r of s equal to omega square n divided by s square plus 2 tau omega n s plus omega square n. The power of s is 2 in the denominator term, hence the above transfer function is of the second order and the system is said to be the second order system. The characteristic equation is s square plus 2 tau omega n s plus omega n square equal to 0. The roots of the characteristic equation are shown in this slide. The Laplace transform of the output signal C of t, R of s is the Laplace transform of the input signal R of t, omega n is the natural frequency, Take Laplace transform of the input signal r of t. Consider the equation C of s equal to omega square n divided by s square plus 2 dou omega ns plus omega n square into r of s. Substitute r of s value in the above equation and do partial fractions if required, and then apply inverse transform. Consider the unit step signal as an input to the second order system. Laplace transform of the unit step signal is r of s equal to 1 by s. We know the transfer function of the second order closed loop control system. The transfer function of the second order closed loop control system is given in this equation. Case 1, for tau equal to 0 and substitute tau equal to 0 in the transfer function, we get C of s equal to omega square n divided by s square plus omega square n into r of s. Substitute r of s equal to 1 by s in the above equation, we get C of s equal to omega square n divided by s into s square plus omega square n. Apply inverse Laplace transform on both the sides. We get C of t equal to 1 minus cos omega n of t into u of t. The unit step response of the second order system when del equal to 0 will be a continuous time signal with constant amplitude and frequency. Case 2, tau equal to 1. By substituting tau equal to 1, we get C of s equal to omega square n divided by s plus omega n the whole square into r of s. Substitute r of s equal to 1, we get C of s equal to 1 by s minus 1 by s plus omega n minus omega n divided by s plus omega n the whole square. Applying inverse Laplace transform on both sides to the above equation, we get C of t equal to 1 minus e power minus omega n t minus omega n t e power minus omega n t into u of t. The impulse response of the second order system can be obtained by using any one of these two methods. First one is follow the procedure involved while deriving step response by considering the value of r of s as 1 instead of 1 by s. The second one is do the differentiation of the step response. The following table shows the impulse response of the second order system for 4 cases of the damping ratio. Damping ratio, it's depend on the value of damping ratio. The second order system can be classified into undamped, underdamped, critically damped and overdamped, as we already saw. The roots of the characteristic equation is given by s equal to minus dou omega n plus or minus omega n square root of dou square minus 1. The roots of imaginary when tau equal to 0. The roots are real and equal when tau equal to 1. The roots are real and unequal when tau greater than 1. The roots are complex conjugate when tau lies between zeros and 1. Undamped system. Step response of undamped second order system is given as C of s by r of s equal to omega square n divided by s square plus 2 dou omega ns plus omega square n. When tau equal to 0, the C of t equal to 1 minus cos omega n t is given by taking the inverse Laplace transform for C of s by r of s equal to omega square n divided by s square plus omega square n. Underdamped system. Step response of a second order underdamped system is given by C of s equal by r of s equal to omega square n divided by s square plus 2 dou omega ns plus omega square n. By taking partial fractions and inverse Laplace transform, we get C of t equal to 1 minus e power minus dou omega n t divided by square root of 1 minus dou square into sine of omega d t plus del theta. For critically damped system, the step response of a second order critically damped system is given as C of t equal to 1 minus e power minus omega n t minus omega n t e power minus omega n t. The graph shows the critically damped system. for undamped, underdamped, critical, and overdamped. Thank you.